Hello everyone, welcome to Calc Lesson number 5. Today we are going to be looking at section 1.4, talking about continuity and one-sided limits. So let's start by talking about continuity. A function is continuous at x equals c if there is no interruption in the graph of f at c. Basically, a continuous graph is unbroken at c and there are no holes, jumps, or gaps. If the entire graph can be sketched without having to pick up your pencil, then it is continuous. The example below identifies three values of x at which the graph of f is not continuous. At all other points in the open interval from a to b, the graph of f is uninterrupted and continuous. So looking at these three examples, in the first, notice we have a hole in our graph. So we would be unable to graph that without picking up our pencil. So that hole makes it not continuous at x equals c. In our second graph, we have the limit from the left approaches a different value than the limit from the right. We refer to this as a jump, which we also could not sketch without picking up our pencil. So this is not continuous at x equals c. And then finally, we have a gap where we have a hole in the middle of our function, and then we have a defined point elsewhere. So again, we could not sketch this without picking up our pencil, so this is another example of a function that is not continuous at x equals c. So let's quickly just formally define continuity. So for continuity at a point, a function f is continuous at x equals c when these three conditions are met. So the first thing that needs to happen is that f of c is defined. Secondly, the limit as x approaches c of the function f of x exists. And finally, the limit as x approaches c of the function f of x is equal to f of c. Additionally, a function is continuous on an open interval, a to b, when the function is continuous at each point in the interval. A function that is continuous on the entire real number line is continuous everywhere. Consider an open interval I that contains a real number c. If a function f is defined on I, except possibly at c, and f is not continuous at c, then f is said to have a discontinuity at c. Discontinuities fall into two categories, removable and non-removable. Removable discontinuities are holes that result from the cancellation of common factors from the numerator and the denominator. This hole is a removable discontinuity. Non-removable discontinuities are vertical asymptotes, which make the denominator equal to 0, and jumps or broken graphs. This jump is a non-removable discontinuity. In example 1, we want to use the graphs below to determine the limit at each given c value and then discuss the continuity of the function. So for the first one, for letter A, we want to find the limit as x goes to, and here we have our c equals -1, so -1 of this function. Remember, to find the limit, we want to look at what our function is approaching from both sides of the x values, so looking from the left and from the right, from both sides, our function is approaching the value of 2. When we're looking to talk about continuity, we want to look for any possible discontinuities, so we're looking for holes, gaps, or jumps. Since we would be able to graph this entire function without picking up our pencil, we can say that this function, f of x, is continuous everywhere. Looking at part B, here we want to find the limit as x approaches, this time c is equal to 1 of this function. Remember, in order for the limit to exist, the left-hand side limit has to equal the right-hand side limit. In this case, our left-hand side limit is approaching 1, while our right-hand side limit is approaching 2. Since our left-hand limit does not equal our right-hand limit, this limit does not exist. To discuss the continuity of this function, we can see that we would not be able to graph this function without picking up our pencil because of this jump or broken graph. So we would say that our function f of x has a discontinuity, and specifically since it's a jump, we're going to call this a non-removable discontinuity at x equals 1. Finally, in part C, we want to find the limit as x approaches, and here our c value is 1 of our function. Even though we have our point defined at 1, 2, looking for the limit from the left-hand side and the right-hand side, both are approaching, or in both cases our function is approaching 4, so the limit as x approaches 1 of this function is equal to 4. In looking to discuss continuity, again, we wouldn't be able to graph this entire thing without picking up our pencil because we have this gap where we have a hole and a different defined point. So we would say that our function f of x has a removable discontinuity at x equals 1. In example 2, we want to find the x values, if there are any, at which f is not continuous. If the graph is not continuous, we want to determine whether there is a removable or non-removable discontinuity. So remember, our discontinuities come from holes in our graph, jumps, gaps, or vertical asymptotes. So looking at letter A, here we have f of x equals x squared plus 5x plus 3. Thinking about this quadratic equation, there's no vertical asymptotes, nothing to cancel, so we're not going to have any holes. So this function, f of x, is continuous everywhere or from negative infinity to positive infinity. Similarly, in part B, we have f of x equals sine of 4x. Thinking about what that graph looks like, we have no asymptotes, no holes, no jumps, no gaps. So this function is also continuous everywhere or from negative infinity to positive infinity. Now when we look at part C, here we have a function f of x equals x over 1 minus x squared. So we want to think about any holes, gaps, jumps, or asymptotes that we might have. Remember, vertical asymptotes we get from our denominator equaling 0. So we want to start by just factoring our denominator. So I'm going to write this as x over, and 1 minus x squared is just a difference of 2 squares, so I'm going to write this as 1 plus x and 1 minus x. This tells me that my vertical asymptotes would be at x equals 1 and x equals negative 1. So I know that my function f of x has discontinuities at both of those values, and remember, vertical asymptotes are non-removable. So f of x has non-removable discontinuities at both x equals 1 and x equals negative 1. In letter D, we have a very similar function, f of x equals 3 over x squared plus 5x. Again, want to think about this function and find where we have any holes, jumps, gaps, or asymptotes. Again, I'm going to take my denominator and factor it, so I'm going to write this as 3 over, factoring out an x. I have x plus 5 left over. This tells me that my vertical asymptotes, remember you take each factor in the denominator and set it equal to 0, would happen at x equals 0 and x equals negative 5. Again, since vertical asymptotes are not removable, non-removable, we would have our function f of x has non-removable discontinuities at both x equals 0 and x equals negative 5. Finally, in letter E, we have our function f of x equals x plus 5 over x squared plus 2x minus 15. Again, just looking for holes, gaps, jumps, or any asymptotes. Just like in the last couple, we can start by factoring our denominator. So we have x plus 5 over factors of negative 15 add up to positive 2 are going to be a positive 5 and a negative 3. Hopefully we notice that we have the same factor in the numerator and the denominator, so we can cancel that out. And when we do, we're actually creating a whole at x equals negative 5. And then since we still have that factor in the denominator, we also have a vertical asymptote at x equals 3. So this function f of x has a non-removable discontinuity just like in C and D, where we have that vertical asymptote at x equals 3, and a removable discontinuity where we have that whole at x equals negative 5. Now we want to talk about evaluating one-sided limits algebraically. We have already found one-sided limits from a graph by checking how the function behaves from the appropriate side. Most one-sided limits can be calculated algebraically so long as the answer is defined, and the various algebra techniques that we've already learned are still going to apply. So for our first example here, letter A, the limit as x goes to 4, that plus sign, remember, means from the right of x over x plus 4. Just like we could before, we're going to use direct substitution. So we're going to plug in our 4 over 4 plus 4. So we get 4 over 8. So this limit, as x approaches 4 from the right, is going to equal 1/2. In part B, we want to find the limit as x approaches 1 from the left of x minus 1 over 1 minus x squared. Using direct substitution, we get 0 over 0, our indeterminate form, which remember is a big hint that we have a little bit more work to do before we find our answer. In this case, we want to use our factoring and canceling technique. So I'm going to take that fraction and rewrite it as x minus 1 over my denominator, 1 minus x squared. It's just a difference of squares, so I can write this as 1 minus x, 1 plus x. Looking at the factors that I have, I notice that I have opposite signs in one of my factors, so I'm going to factor a negative 1 out of my numerator. Changing both signs, I would have negative x plus 1, which I could also write as 1 minus x, over 1 minus x times 1 plus x. Now I notice I have the same factor in my numerator and my denominator, so I can cancel those out. Remember, that is a whole in my graph. So I can write this as negative 1 over 1 plus x. Now that I've simplified, I can use direct substitution to plug in that value of 1. So this becomes negative 1 over 1 plus 1. So my limit as x approaches 1 from the left is going to be negative 1 over 2. Finally, looking at part C, I have the limit as x approaches 0 from the left of the function the square root of 4 plus x minus 2 over x. Again, using direct substitution, when I plug in a 0, I get 0 over 0, a big hint that there's a little bit more work to do before we can be done. In this case, because I have the radical in the numerator, I'm going to use that rationalizing technique that we learned a couple of days ago. To do that, remember, I'm going to take my function, the square root of 4 plus x minus 2 over x, and I'm going to multiply by the conjugate. Remember, the conjugate takes the two terms that you already have and just changes the sign in the middle. So we're going to multiply by the square root of 4 plus x plus 2 over the square root of 4 plus x plus 2. When you multiply through your numerator, remember you're foiling or creating a difference of squares. So when we square the first term, the square root of 4 plus x squared just gives us 4 plus x, minus when we square our second term, 2 squared is just 4, over, and then our denominator would just be x times the square root of 4 plus x plus 2. Simplifying our numerator, we have a 4 minus 4, so those are going to go away. And we are just left with x over x times the square root of 4 plus x plus 2. Again, our x in the numerator and denominator are going to cancel out, so we have simplified our function down to 1 over the square root of 4 plus x plus 2. Now that we've simplified, we can use that direct substitution. Plugging a 0 in, we would have 1 over the square root of 4 plus 2, and of course the square root of 4 is just 2, so we have 1 over 2 plus 2 is 1/4. The last topic we're going to look at today is evaluating piecewise function limits algebraically. So if the function in question is a piecewise and the limit is one-sided, you only need to test the value from that side. If it is a regular limit, you must test each piece and compare them to ensure that they match or the limit does not exist. Creating a graph of the function is helpful, but not necessary in this case. So we're going to look at example 4. We're going to find each limit if it exists and then evaluate the continuity. For letter A, we have our function f of x is defined as x squared minus 4 when x is less than 2, and x is greater than and negative x plus 3 when x is greater than or equal to 2. So we're going to find each sided limit and then our regular limit. So looking at the limit as x approaches 2, remember the minus sign means from the left, which means we want to look at values that are less than 2. So for this limit, we're going to be looking at that top function, that x squared minus 4. Using direct substitution, we can plug in 2 squared minus 4 gives us 4 minus 4, so the limit from the left-hand side is equal to 0. From the right-hand side, we want to look at values that are greater than 2, so we're going to be using the other function, so our plus, remember, means our right-hand side. We're going to be using that second piece, that negative x plus 3. Again, we can use direct substitution here, so we can plug in negative 2 plus 3. So our limit from the right-hand side is equal to 1. Because the left-hand side limit does not equal the right-hand side limit, the limit as x approaches 2 does not exist. So then thinking about what this graph would look like, our limit approaching from the left is approaching 0, our limit from the right is approaching 1. So we actually have a jump in our graph at x equals 2, so our function is not continuous at x equals 2, and since it's a jump, we're going to call that a non-removable discontinuity at x equals 2. And for our final example, we just want to look at this piecewise function. Here we have our function f of x equals 5 when x is less than or equal to 3, and negative x squared plus 14 when x is greater than 3. So we're going to start by looking at the limit as x approaches 3 from the right-hand side, meaning from the values that are greater than 3. To do so, we're going to use that second function, that negative x squared plus 14. We're going to plug in or direct substitution for our value of 3. So we have negative 3 squared plus 14 gives us negative 9 plus 14. So the limit as x approaches 3 from the right of this function is just equal to 5. We also want to look at the limit as x approaches 3 from the left, which means we're looking at the values that are less than 3. To do this, we're going to look at that top function, since here we have x defined as less than or equal to 3. And that function is actually just equal to 5, so not too much work to be done there. Finally, we want to look at our regular limit as x approaches 3. Remember, in order for that limit to exist, the left-hand side limit has to equal the right-hand side limit. Since our left-hand side limit is equal to our right-hand side limit, in this case, both are equal to 5, the limit as x approaches 3 of this function is just equal to 5. Now we want to look if our function is continuous. Remember those 3 conditions from the beginning. The first is that at x equals 3, our function has to be defined. So f of 3 is defined. If we look at our piecewise function, when x equals 3, our function will equal 5. We also want to check that the limit as x approaches 3 of this function exists, and in this case it equals 5, so it does exist. And finally, we want to check that our limit as x approaches 3 of this function is equal to what our function is defined at 3, so f of 3. Both are equal to 5, so we satisfy all 3 conditions. So yes, this function is continuous at x equals 3. Great job with this lesson. If you have any questions, you can reach out to your teacher. Now you are able to complete homework number 5, which is in section 1.4, pages 79 and 80, numbers 2 through 5, 8, 10, 12, 16 through 20, 27 through 30, 35 through 49, 52, and 53.